Hi, good evening or good morning, and thanks everyone for joining TinyML Talks today. This is the last meetup for the year of 2021, and this is the first inaugural meetup hosted by TinyML community in Ukraine. I'm Oleg Boguslavsky, and I'll be the moderator of today's session. And the topic of today's session is practical TinyML for industrial safety and personal performance monitoring. The presenter will be Oleg Puzanov, CEO of Leantegra. But first of all, let me tell a few words about our partners and strategic partners of the TinyML community, which is growing literally every day. So our strategic partners are Aeon Devices, ARM, DeepLight, Edge Impulse, EMSA Visual Sense, Greenwave Technologies, Groovity Incorporated, HOTG, Imagimob, Latent AI, Maxim Integrated, now a part of Oleg Devices, a company called Quixo, Qualcomm, Reality AI, Renesas, Rixon, SAP, Seed Studio, SenseML, Stream Analyze, Life Augmented, ST, SynSense, and Sentient. And we always have additional sponsorships available. So you can write to Olga at tinyml.org for the additional information. As you can see, the list of strategic partners is expanding literally every month and every meetup. We'll have a huge 2022 TinyML Summit held on March 28th to 30th. And Hyatt Regency San Francisco Airport, so the meetup will be held in person. So we really hope that all these COVID issues, they won't prevent us from making all these dreams happen. The registration was open till December 15th, and the deadline for postal submission is already passed, so it was due to December 17th, but you still try contact for the sponsorships options, or maybe if you have something really extraordinary. There are a couple of nominations, the best product of the year and the best innovation of the year, and you can apply for these awards between November 15th and February 28th. The first day of the summit will be the TinyML Research Symposium, and the call for papers was also due to December 17th, so I think everything is already set. And we really hope that it will be a great event, and we hope that we'll be able to see everyone in person. As I mentioned, this is the last TinyML Talks for this year, so I would like to say very happy holidays to everyone. And the next event will be right after the New Year Eve on January 4th. The presenter will be Cedric Nutteren from Plumerai, and he will be demoing the world's fastest inference engine for ARM Cortex-M. It will also start at 8 a.m. Pacific time, and I'm pretty sure that many of you would like to present on TinyML Talks, so you can contact talks@tinyml.org if you're interested in presenting. Let me tell you a few words about Ukrainian org committee. I'm very thankful to my colleague Sergey Kashenko, who is CEO at Yellow. This is a very big, fast-growing crypto community, yellow.com, who helped to establish the community in Ukraine and actually to prepare the meetup today. And as I mentioned, I'm Oleg Boguslavsky. I'll moderate today's session. I'm co-owner of Data Science UA. Our company provides the variety of services around data science, AI, and ML. So we do consulting. We are building offshore teams for clients from EU, US, UK. We can build literally the team of any size for you who will do the software development, hardware development, whatever you may need. And essentially, our company builds the ecosystem, and with our local community of machine learning engineers, which is more than 10,000 people in Ukraine, we are really happy to be partnering with the TinyML. And thanks a lot once again for joining today's meetup. And now I'm very happy to present our speaker today. Coincidentally, he's also Oleg. So our speaker today is Oleg Puzanov. He's CEO and co-founder at Leantegra. He is working around 20 years in commercial IT projects and companies. He's my colleague in the sense that we both worked in the embedded area for many years. He has a great sports history in terms of Ironman and ultra marathons and all the other things. And the products which are produced by Leantegra are really exciting, and I'm very happy that one installation of Leantegra product is actually in our office right now. We one of our clients is also testing this solution right now, and it's very competitive. That's what I can tell for sure. So I'm very happy to pass the word to Oleg, and let's start our talk today, and hope you'll be proactive and ask more and more questions. Thanks a lot.
So thank you, Oleg. Thanks for the intro. I'm glad to be here today, and thanks to all for joining today's session. So our topic for today is about practical examples of using TinyML for industrial projects. And our story, the story of our company about why and how we integrated TinyML into our products. So at first, a couple of words about our company, Leantegra, who we are and what we do. So our main focus is about developing software and hardware for RTLS. RTLS stands for real-time location systems. It is about tracking location indoors, inside buildings where regular GPS doesn't work. For that purpose, we are using different wireless technologies based on BLE, ultra-wideband, Wi-Fi, LTE, and so on. We have specific algorithms for the purpose of location tracking based on all these wireless technologies. And typically, we install our equipment and deploy our solutions in different industrial locations, such as underground mines, factories, warehouses, and so on. So to jump straight to a case study, so you'll have a bit better understanding what kind of projects we have. So this is our project for one of the largest customers here in Ukraine. The company's name is DTEK. It's one of the largest company in the energy sector. They have different underground mines, like coal mines. And our project, which was successfully deployed and launched, was about more than 2,000 BLE beacons and 1,700 smart lamp devices, which are just advanced cap lamps for miners. So all those devices were successfully installed and launched underground inside the coal mine for the purpose of employee safety for underground miners and location tracking. So we are tracking location with an accuracy of 10 meters, doing telemetry for methane and other use cases. So we used here our proprietary algorithm based on reverse BLE RTLS, and the main advantage here is that for RTLS installation, we did not require any cables. It was a very quick process. We just installed some BLE beacons, and that's it. We had the ready RTLS solution inside the mine. Some other names of our customers and partners. Typically, we work through system integrators in different regions who help us to install and to maintain systems locally for the end customers. So speaking about Leantegra hardware and software, here you can see some examples of devices which we design and develop. We have an in-house engineering team for hardware and software. So some examples here like ATEX BLE beacons, which are suitable for installations in highly explosive mines like coal mines, IP67 industrial grade BLE beacons, RTLS anchors for ultra wideband and BLE, and some more specific and specialized devices such as embeddable locators for cap lamps based on LTE and Wi-Fi. And I want to discuss these two devices in some more details because the demonstration of using TinyML for our platform will be based on these two specific devices. So these devices are PCBs with Wi-Fi or LTE and also BLE on board, which are embedded inside the casing or inside the enclosure of the cap lamp. So this specific device, which I'm showing now on this slide, was deployed for one underground mine in Bulgaria. There was a private LTE network which we deployed together with our partners, and this device connected to the private LTE network for data transfers. Plus, there were some BLE beacons which were installed inside the mine, and this device, it was collecting BLE signals for the purpose of location tracking. Another similar device was based on Wi-Fi and BLE. The idea here is the same. Some beacons are installed inside the mine. The device, which we call locator, collects BLE signals, then applies some algorithms for location tracking and delivers location data using industrial Wi-Fi. By the way, for the DTEK project, we also had the deepest industrial Wi-Fi installation underground, which was more than 500 meters at the time. In addition to hardware, we also have software, just some screenshots for you to have basic understanding what kind of features and products we have. So this is our web portal. You can see that it has mapping features to show location of assets and people on the map. Then you can search for people or assets using search box by the name or by personnel ID. Database of employees, historical information like historical track, which shows a trajectory, how a person walked, let's say, during the last several hours. And here you can see on this screenshot, the so-called multi-layered map. You can enable or disable different features on the same map. For example, you can view locations of all beacons on the map, of all people on the map, or even methane telemetry on the same map. So pretty advanced end-to-end platform with all components in place, which you need typically for RTLS system to run. Just to summarize just a couple more slides about our company, and then I'll continue to the TinyML topics. We also have some R&D activities to design our own algorithms, both for RTLS and ML, like this RTLS algorithm, which we called wireless ultra-wideband TDOA, which is a completely wireless and asynchronous DA algorithm, which doesn't need precise clock synchronizations among RTLS anchors. So if you are familiar with the topic of TDOA RTLS, maybe you heard that normally TDOA anchors, they require very precise clock synchronizations, like down to 1 nanosecond. With this new algorithm, there is no need to synchronize all the RTLS anchors. It means simpler installations, less expensive network equipment, and overall less risks on the projects. Another example of our proprietary algorithm is the reverse BLE RTLS, which I described about the project for DTEK. So it's a very simple, from high-level perspective, algorithm, which is just a one-dimensional RTLS algorithm, which shows where you are positioned along the tunnel, right? But this algorithm and this system based on reverse BLE RTLS, it has a very strong advantage that its installation doesn't need any cables. So less expensive, easier installation, less risks for everybody. Now, I think this is it about our company and products. If anybody has any questions about Leantegra overall, our products, RTLS, then I would be glad to answer.
So far, I don't see any questions in the Q&A and in the chat. So now I think we'll switch to the ML part. I'm pretty sure that we'll have a little bit more questions.
Okay, perfect. So let's start with some basic theory about IMU. So IMU stands for Inertial Measurement Unit, or some people just call it accelerometer, but normally it includes some other components like a gyroscope, magnetometer, or barometer. Let's use IMU just as a common name. But what are the typical components or devices which enable motion tracking, right? The first one is accelerometer. I think many of us familiar or heard, right, about such kind of devices. It allows measuring linear acceleration. There are different small details which should be considered, like you should subtract the gravity component from accelerometer to measure acceleration more precisely. And there is also a detail which is called zero-G offset, because some accelerometers, they might have different deviations from the perfect measurements. Then gyroscope, it measures angular velocity, right, the orientation or the rotation of the device. Magnetometer, based on the Earth magnetic field, it can measure the strength of magnetic field and orientation, right, like a compass pointing north, south, west, or east. And the fourth kind of device is barometer. It measures the pressure, right, and enables measuring altitude or height of the device. Plus, maybe also saw different configurations for IMUs like 3-axis, 6-axis, 9-axis, or the so-called 3DOF, 6DOF, and so on, degrees of freedom. Those abbreviations simply mean that, for example, 6DOF includes both accelerometer and gyroscope. 9 degrees of freedom IMU includes accelerometer, gyroscope, and magnetometer. For the case of our devices, we use 3DOF, 6DOF, and 7DOF. And now some additional details. So this is what we use in our devices. We have both simpler and cheaper models for IMUs, like the one from ST Microelectronics, and more advanced and feature-rich IMUs from Bosch, both IMUs and barometers. So our previous older devices used the 3-axis accelerometer without any gyroscopes. But all the newer models, they're using both IMU with gyroscope and accelerometer, as well as barometer. So IMUs are not just for motion recognition, right? We have some other use cases and usage scenarios for IMUs, like IMUs really help to save battery for RTLS tags and BLE beacons. We have a feature on, for example, on our ultra-wideband tags, which we call adaptive transmission. So it's about changing the transmission rate for RTLS devices based on the presence or absence of the motion. It means that when there is no motion, there is no need, right, to send a lot of RTLS data, because we understand that nothing moves, right? In this way, we send less frames wirelessly and we save battery. Just to compare, with adaptive transmission, we are able to save, I think, up to 5 times of battery life, just by using IMU, right, together with RTLS. Then we are also using IMUs and accelerometer for Kalman filtering in our RTLS algorithms to enable smoother experience and smoother data for trajectories, because sometimes the dot on the map, it might jump, right? And in the end, that's the main topic for today. We use IMU data for motion recognition using on-device ML based on TensorFlow Lite and Edge Impulse software. But why, why is a good question? Why do we need on-device ML? Why we cannot just send raw data to the cloud or to another edge server for local processing? Why do we need to handle the execution of ML functions directly on, tiny MCUs like Cortex M0, which we have, or NRF52? So some advantages and some reasons on the slide. So the first advantage is that we enable major power savings thanks to on-device ML. Very good example is about ultra-wideband RTLS, that by integrating TinyML into our ultra-wideband RTLS tags, we saved up to 5 to 10 times of battery life. Once again, up to 5 to 10 times. That's a lot. That was done by sending smaller ultra-wideband frames and sending less ultra-wideband frames. It means smaller transmission rate. Because if you keep streaming raw ultra-wideband data like all raw data from accelerometer through ultra wideband, basically your battery can die in 1 week or even faster, because ultra wideband radio or RF part is very power hungry. I think, as I remember, our devices at the peak transmission rate for ultra wideband, they consume up to 70 milliamperes. That's a lot. But once again, by using IMU data, and on-device ML, we are able to send only the recognized events like motion types without streaming all the raw data. That's the first advantage. The second advantage is about latency. As we all understand, all those handshakes between devices and servers through protocols like MQTT or HTTP, they consume time. And if you have a really tough real-time system with tough constraints for the latency, those client-server systems might not be the optimal option. So everything should be processed locally on the devices. So for the case of our systems, we are aiming, that is still not implemented, but it's in progress. We're aiming to enable sub 10 milliseconds scenarios for feedbacks, like haptic feedback using Vibra modules for ultra wideband tags, or emergency braking for collision avoidance. This is about understanding that there is a person in front of a vehicle, for example, right? Let's say inside the factory or inside the mine, and that you should apply emergency braking, automatic braking to the vehicle very quickly. You don't have any luxury, right, to ask the server to process your data and then request the reply, because it might take how much time? 100 milliseconds for the case of local network, maybe even 1 second for the case of cloud server. But here, if we do on-device ML and do detection locally, then we can achieve sub 10 milliseconds easily. And the third advantage, it is about offline mode. It is about keeping devices operational even when there is no network coverage, like no Wi-Fi, no LTE, but still you need to enable operations of your devices, right? Like it's important for life critical systems, plus sometimes you don't have coverage everywhere. Like our project for underground mine, it doesn't have 100% Wi-Fi coverage. I think it's like 80% of the mine is covered with Wi-Fi. Still, it doesn't mean that devices should not function where there is no Wi-Fi. For this purpose, we're using offline mode, where we collect RTLS data. We do the so-called buffering, right? Plus all the on-device ML functions also work even without any kind of networks, because all the algorithms are based on TinyML and they are being processed locally without any servers. So we had a very special story about deploying and integrating TinyML into our hardware. We started the first experiment, let's call it like this, about motion recognition on-device ML around 2 years ago, maybe 2.5 years ago. At that time, I think there was no TinyML, maybe didn't hear about TinyML. So we decided to implement our own custom code for motion recognition on our beacons, BLE beacons. Here on the photo, you can see the device, which is called YB 2.0. It's a BLE beacon based on the Nordic NRF chipset. BLE 5.0, it also has accelerometer on board, no gyroscope. That's why we had some limitations for the algorithms here, but still the initial implementation worked fine. We didn't use vectors or any kind of orientation matrices here. It was a pure scalar approach. We just took the square root of all acceleration values, subtracted the gravity value, and that's it. It worked fine. No standard algorithms here, no standard tools like TensorFlow Lite. It was a very simple, very small piece of code. I think it utilized k-means clustering, maybe the only part from standard formulas. Everything else was very custom. But still, it worked completely on device without any kinds of servers. And here you can see a demo about how it works. So this is our office. In the left corner, you can see some logs from the device, which does classification of the motion here. So now we have a walk kind of motion, which was recognized. And she carries beacon in her hands. Now we have fast walk, almost running, then regular walking. That's true. Okay, now we have running, one false detection because the system thought that it was a fault detection, but it was not. Then idle again, and now we have running. So I should say the first version was 90% accurate, which is not bad, you know, for the very first implementation, without any kind of frameworks. 1 second.
Yeah, Oleg, meanwhile, we have a couple of questions coming from our participants. The first question is the technical one from Oleg Zhubin. Is it possible to use magnetometers underground in tunnels?
Yes, it's possible. You're right. We had a similar question whether, you know, there will be any kind of, you know, interferences underground, especially in iron ore mines, because for coal mines, by default, it seems to be fine. But, you know, iron ore mines, they have a lot of magnetic interferences. So we expected magnetometer to be useless inside the mine. But according to our brief tests, it can be used, though we don't have any plans to use it. So right now, what we have is enough. I mean, accelerometer, gyroscope, and barometer.
Okay. The next technical question is, what is the battery life of the BLE beacon? So I know the answer that it really depends on the mode, precision, and other things, but I'll let you to answer this question as well. So what's the approximate battery life for the BLE beacons?
This is a very good question, and I should say it varies. Our industrial and ATEX compliant beacons, they have the battery life at least of 2 years, 24 months. This beacon, by default, it has the battery life of 12 months, but by varying the parameters, right, you can decrease the blink rate, it means the transmission rate, and save some battery. So to answer your question, the battery life varies from 1 year to 2 years. There are some other beacons on the market which claim 5 years or 7 years. I don't believe that it is practically achievable to get 7 years of battery life on the same battery, because, you know, the battery itself, it would simply die within 7 years, right? But I think 3 years, maybe to 4 years
okay,
maximum.
thank you. Yeah, thank you very much. Yeah, thanks, Oleg. One more question. Did you try LoRa instead of Wi-Fi or LTE in tunnels? LoRa.
LoRa, yes, I'm aware of the protocol, and we had such thoughts. So why we decided to use Wi-Fi? Because the customer requested also voice and video calls based on the same network, right? Not just telemetry from sensors, but also voice and video. And as you understand, LoRa and its throughput is not suitable for voice and video. That was the only reason.
Yeah, true. Maybe for some extreme low rate speech codecs it might be, but definitely not for the something serious.
Exactly.
And there are 2 more questions actually. So the next question was also from Alexander. Where Kalman filter is implemented? Is it running on each variable node or on each beacon or in central system manager nodes? I think that this question was already addressed, but just to double check.
So Kalman filter relates to our RTLS algorithm, not to motion recognition, because for motion recognition we are using TensorFlow Lite without any kind of Kalman filters. But for RTLS we have an edge server, a locally installed server using C++ and JavaScript code, right? It gets raw data from RTLS anchors, right, and applies Kalman filtering for data processing. So to summarize, the current version of our system has Kalman filter on the edge server, not on the MCU devices.
Okay, thanks very much, Oleg. And the next question is kind of similar, but probably with a different answer. So the question was, does any of your devices deploy TinyML algorithms directly on the IMU sensor for ML inference and energy savings like the STM's IMs?
Yes, true. And my next slides will describe the whole setup, right, and our process of deploying a TinyML to our devices.
Okay. Yeah, thank you very much. Again, a couple of technical questions from Mr. Cross. How do you charge or replace batteries on the devices? There are like four more questions after that. So maybe let's address this question, and after that we'll let you continue, and after that we'll come back with the questions, with the remaining questions.
Question, how do we recharge batteries, right, on RTLS devices? So we have several models for devices. One of our models has a wireless charging based on Qi standard. You know, you just put a device on a wireless charger, like for an iPhone, and that's it. Some other devices have a magnetic connector. Like if you've been using, let's say, sport watches, GPS watches, you know, they have similar type of connectors. And for BLE beacons, especially the ones which are shown before, the battery is just replaceable. It's not rechargeable. You just buy a battery, let's say CR2477, right? You use it for 1 year, 2 years, and then you just throw it away.
Yeah, that makes sense. Again, considering the characteristics of the battery, sometimes it's even more beneficial.
Yeah, the battery
thanks a lot, Oleg.
50 cents, you know, not very expensive.
Right. Okay, thanks a lot, Oleg. Just go ahead with your presentation, and after that, I'll ask you the remaining questions.
Thank you. Now, I think the most interesting part starts, because yes, I tried to represent the whole story, why and how we reached the point that we need to start integrating some standard frameworks and standard tools for on-device ML, you know, from the TinyML ecosystem. So last year, we decided to redevelop our on-device ML based on the standard platforms like TensorFlow. So as a result, what we took TensorFlow Lite Micro. We also decided to take Edge Impulse software as a service, which is a great portal and platform for training, building, and deploying ML models for your tiny devices, like MCU-based devices. So we took TensorFlow Lite, we took what Edge Impulse has, we customized a bit some code for the specifics of our hardware, and now we have our own framework, which we called TagML, just a slightly customized TensorFlow, you know, suitable for ultra-wideband and BLE devices of Leantegra. So yes, it works now. It enables cool time-critical detection scenarios. But the main point here is that we enabled standard and universal tools, right, without any kind of custom coding. So now even our customers or partners can train new ML models by themselves without any need, you know, to write any code. Now it's very easy to do, and I'll show you how it is done. So this is how the end-to-end deployment process looks like. It might look complicated, you know, with all those steps and boxes scenarios, but I think it's not a very advanced process. So the first step, it's about collecting and labeling data, right, for training. So here we just use, let's say, the locator for underground mines, which I showed you before, and the mobile app. We have a mobile app which just connects using Bluetooth to the device and configures the kind of motion which we are training now. It can be fall detection, it can be walking, running, sitting, whatever. So you just press and select the type of motion which you're labeling. Then you collect some data. It can be data collected for several minutes. And the device, since it has Wi-Fi on board, right, it sends all the collected raw data, the training data, through MQTT protocol to the broker, which is a server, right? And then we have a Python script, a simple custom Python script, which subscribes to the topics and saves the data from the broker to some CSV files. What kind of data I'll show later. And then we take those CSV files with XYZ data from accelerometer. We upload those files to the Edge Impulse portal, which has a very nice and intuitive interface to build and to train ML models, right, and to deploy them later to TinyML devices. Plus, it can also generate C++ libraries specifically for our kind of chipset, which is Nordic NRF. And then we just compile statically those libraries into our firmware, and that's it, and do the upgrade wirelessly over the air using Bluetooth. That's how the process looks like. Now some more details, because I think, and I'm sure not all things are clear here. Let me provide some more details about the process. So the first step is about data labeling. For this example, we took the helmet, the miner's helmet, with the cap lamp. This is the smart lamp, which I mentioned before. It has that BLE plus Wi-Fi locator for RTLS inside. So we connected, one second. Okay. So we connected to this device using a mobile app and simply set the parameter for the label. It can be again running, falling, walking, whatever, and collected some data. And then this data is being sent from the device through MQTT. You can see some examples here. Just draw XYZ data from accelerometer, and all this data has been labeled for this example as fall detection, fall. So here we have two classes of motions, fall and idle, right? Which we get as a result of collecting data from the device. Then we open Edge Impulse, a web portal. Again, very nice software. I highly recommend this, for TinyML deployment purposes. Then we build the so-called pipeline in the Edge Impulse. The first step is about time series data, which comes from CSV files. We select different parameters here, like window size. Again, the whole data is several minutes, but we need to define the window size. Based on our experience, the right window size is around 2 seconds, 2 or 3 seconds, which is suitable to identify typical motions such as running, walking, falling, and so on. The second step is about spectral analysis. It's about converting time domain data to the frequency domain using, FFT transformations and so on. After the second step, we get some features which are automatically generated for the learning phase based on neural networks. So from spectral analysis block, we go to neural network block based on Keras. And then this is where all the magic about model training happens. In the end, we have the model, which can be tested and validated directly here in Edge Impulse. You can see the sample screenshot, some classes, how they are separated, right, on the plane, very clear separation between fall detection and idle mode for the motion. The accuracy is 98.9%, very good for this example. Yeah, and this is it. It's a very simple process. The next step is about selecting our hardware chipset, which is again Nordic NRF52. We generate C++ library, which is just about matrices, right? Some variables with matrices, and then we compile that C++ library into our firmware, and we are done. In the end, you can see as a result, the device sends RTLS data to our web portal, and the data is visualized. So in addition to RTLS data, like a dot on the map, we also display the motion type here. So here it is walking, or it can be falling or idle. So this is how it works. So nothing complicated, but I think now we have a very standard and clear process and approach to train and to launch models for motion recognition. So any questions at this stage?
Yes, Oleg, there are quite a few questions actually. So the first question is, how do you monitor for device failures, and how do you manage failed devices to keep the system operating? And I think that the question associated with that, do you have to comply with regulatory standards for your devices like OSHA in the US, for example?
Yes, it's a very good question. So to answer the first question about device status monitoring, so on this specific screenshot, you can see some icons. Those are BLE beacons installed inside the mine. You can see some beacons are displayed as red, some beacons as green. So the green beacons are the ones which sent any signals recently, right? And red beacons here, maybe that's because people did not walk near them, right? Or maybe they are just discharged or something. So we have a built-in feature inside our web portal to do device management, right? Like battery life monitoring, on-off monitoring, malfunctions, and so on. That's to answer the first question. And the second question about the regulations. Yes, we, as I mentioned, in addition to basic FCC and C certifications, we also have industry-specific ATEX certifications. It is required for coal mines, right? So all equipment which is installed inside coal mines must be ATEX certified, and each country and each region has its own kind of standards. But for some other locations like iron ore mines or our project in Bulgaria, which was about copper gold mine, it didn't have such kind of regulations because there is no need for ATEX there. So to answer the question, it varies, right? It depends what kind of mine you have, what kind of factory. Again, not all factories require such certifications. Like we have a new project for a steel factory in Ukraine where we do personnel tracking people. So there we don't need any ATEX certification, just C, right? Standard C certification, and that's it.
Okay, thank you very much. The next question is, I think it's also addressed in the presentation, how do you deploy new software versions on all the devices? So I think it was on one of the slides.
Yes, if possible, let me, yes, Oleg, I'm trying to enable full screen mode, but somehow it doesn't work. 1 second, please. Okay, yes. Now I'm back. So sorry about this. I'm trying to go to the right slide. So regarding the firmware upgrades, 1 second. Yes, so all our devices, they're upgradable over there. So devices like BLE beacons or RTLS tags, they support a BLE upgrade. You just take a mobile app, right, and select the device and do the upgrade. If we're talking about larger devices such as RTLS anchors, they have Wi-Fi on board, and then we use TFTP or other typical protocols such as BootP for remote firmware upgrade.
I see. I think. Thank you very much. One more question, and then probably we'll continue with the presentation. So do the devices store data locally and then upload it to the local edge server for analysis when the connection is made?
That is a very good question, because for industrial projects, I think 90% of our customers, they install all their servers locally. They don't have any cloud servers at all, right? They have just their local networks. So they have the LAN with the devices, and they have the edge server, nothing else. It's about security, it's about response time, it's about their IT policies that they don't want to keep anything in the cloud. So to answer the question, we just have typically the devices and the edge server, where both the web portal and the RTLS server is present.
Okay, thank you very much, Oleg. I think that you have roughly 5-7 minutes for the presentation, and there are still 5 more open questions after that, and then I'll have the closing part. Thank you.
Okay, thank you, Oleg. And sorry about that small mess with the slides, but yeah, now I understand how to switch the full screen mode. But overall, I think we are done here. So I explained the end-to-end deployment process, the result, what we get in the end, right, from the on-device ML. Right now, we're also implementing, and it's almost done, the collision avoidance, not just to show some data, because that's not all the beauty of on-device ML, right? You can also collect some data without any kind of on-device processing. You can just send the raw data to the cloud, to the server. But for such systems as collision avoidance, you have no other options just to process everything locally, because you cannot do any kind of communications with the server, because the latency and the time limitations are really, really important, right? You cannot just spend, let's say, 100 more milliseconds when the vehicle, let's say, inside the mine is almost hitting a person right in front. You must track within several milliseconds, right, directly, locally on the device. And as you understand, without on-device ML and without local processing, without any service, right, it's not possible. So this is it about the demonstration. I tried not to make it very complicated. If you have any additional questions, then you can ask them now. Plus, you can also visit our website, which is leantegra.com. And also, I would be personally glad to answer any kind of your questions if you will drop us an email at this address.
Thank you very much, Oleg. I must say that that was an excellent presentation. And for example, one of the comments in the chat from Mark Donaldson is that this is the masterclass on TinyML solution implementation. Really enjoying the presentation. Nice. I think that thanks Mark a lot for these kind words, and we are grateful for all participants. And there are quite a few questions remaining, so there are 6 more questions to address. So let's try to answer them as quickly as possible. So first question from Mr. Kroos. What product do you use for your MQTT broker?
This is a very good question. So we reviewed several options for MQTT. One of them was about Mosquito, an open source broker, but many of our projects, they have the so-called QoS2 level. It's about guarantee for delivering messages at least once, right? So if you're familiar about MQTT, then you understand. If not, it can be easily discovered. But only Verne MQ broker had that feature in place. So we had to select Verne MQ, but still we are very happy. It's very stable, feature-rich broker. So we deployed it, I think, at least on 10 different projects. So once again, it is called Verne MQ. So nice option for the broker.
Yeah, thank you very much. Next question are a little bit more detailed regarding the implementation. So how much data you had to collect for the training production ML model? Was it like hundreds of thousands or more samples?
So for the case of people activities, it is rather about the amount of samples which one person collects. It's about how many people were collecting the training data. Because especially for the case of underground mines, different people carry their helmets in different ways, right? Some people are not even fixing the headlight on the helmet. They might just hang the lamp, somewhere on the neck. And we must also consider such kind of scenarios. Plus, some people might rotate the helmet a bit, and it all impacts the accuracy of recognition. So to answer your question, it's not about the breadth, right, and collecting 1 million of samples. It's about giving the tools to not just one person, but several people, and to consider all typical ways how people can carry the device.
Okay, thank you very much, Oleg. By the way, right now, all participants, you see the poll where you can feel the feedback about the session. So please fill this poll, which appeared via Zoom to you. And meanwhile, we continue to ask the questions. So one more question from Alexander Zhubin. So what is the size of data vector for the FFT conversion? Was it 128 or 256 or 512 samples FFT? So what's the size?
Oh, let me get back to that slide because maybe I cannot recall it. So 1 second. The vector for the FFT, the frequency, it was so since we are dealing with low power devices, right? And we cannot afford luxury of 50 hertz or 100 hertz or more for accelerometer. We have two modes. We have the default mode, which is 12.5 hertz, right, for accelerometer, and we have 25 hertz, a bit more advanced. And as we see now on practice, this is enough. Yes, ideally, the more frequently you collect the data, right, like 100 hertz, 200, it's better, like the accuracy is better. But you must also consider the battery life and find the right balance between the accuracy, right, and the battery life. So to summarize, based on our experience, using 12.5 or 25 hertz for accelerometer data is enough for typical motion recognition purposes.
Well, thank you very much, Oleg. Please also give me the control. And the next question is, what is the typical model size for this application? How much memory is typically required? So it's a very good question, actually.
I think we have some numbers here, even in terms of RAM memory. I mean, it's several kilobytes. In terms of flash, yes, so we have some numbers. Peak RAM usage is almost 2 kilobytes, and flash usage is 20 kilobytes. Pretty suitable, for mid-level MCU right here.
I see. Okay. Thank you very much. The next question from Mark Donaldson. Your devices deal with human assets and human safety for RTLS. So do you plan to incorporate 5G in your future releases?
Actually, we already have one ongoing project about 5G based on Quectel modules, 5G Quectel. I cannot disclose that much of details because of NDA, but yes, we have some plans to use 5G, not for indoor positioning, because ultra-wideband RTLS has a better accuracy than 5G. Ultra-wideband has 20 centimeter accuracy and 5G has several meters, maybe 1 meter, but not better. So for data transfer purposes, low latency data transfer, yes, 5G is good. For RTLS itself, 5G is not the best option for now.
Okay. Thanks, Oleg. And the last question for today, and please give control over the presentation in Zoom. So the last question is, for collision avoidance, all moving vehicles should have beacon mounted, and all people in the tunnel should have wearable beacons, right? So I assume that there are some other parts where you install the beacons besides the moving parts and people. Are there any others?
So the question is, in which places inside buildings or underground we install beacons, right?
Right.
So, well, it depends on the algorithm. Sorry, maybe I should go back to the slide about the RTLS algorithm here. 1 second. Yeah. So for the case of this algorithm, which is called reverse BLE RTLS, we just need to install beacons along the tunnels or inside rooms where we track people. For the classic RTLS algorithm, or the so-called forward RTLS, the people are carrying beacons or bracelets, and the RTLS anchors or locators, and by saying locators, I mean, sorry, again, these devices, right, which do tracking. They installed on ceiling. So just, to summarize, there is a classic RTLS and reverse RTLS. For the case of reverse RTLS, which you're using inside mines, the beacons are mounted, they're fixed inside the mine. And for the case of classic RTLS, people are carrying beacons or tags inside pockets or as bracelets.
Okay, thank you. And still we have more and more questions coming. So the last two questions for today. So how do you measure success for deployment of this system?
How do we measure success? Well, it is about being compliant with customer requirements, right? Normally, it is about location accuracy. It's about recognition accuracy. It is about non-functional parameters for devices such as battery life, because to be honest, sometimes it is a challenge to keep 2 years for beacons because of different characteristics, like it might be extra water inside the mine, the temperature might drop And as you know, maybe as you know, battery life, it depends on the temperature. The lower the temperature, the less you will get in the end for the battery life. So to summarize, it's about functional requirements like location accuracy, recognition accuracy, and also non-functional ones such as battery life, stability, and so on.
Okay. And one more question is, how do you use the supplier to build your devices, or do you acquire parts and build them yourself? So it's about the manufacturing of your solution itself.
So the PCBs, they are designed by us, and the firmware for devices, it is also developed by us. We only outsource mass manufacturing. We have one very good partner in China, in Shenzhen, right? We send our PCB files and they do mass production for us.
Okay. Oleg, once again, thank you very much for your presentation. It was very interesting and very useful meetup, and I hope that people who were there live and who will watch the video on the YouTube and watch the PDF file, they'll be definitely interested and they will be in touch with you. And once again, let's go back to the TinyML strategic partners, because with their help, the community grows, expands, and with their help, we are able to make such great meetups. So I would like to mention each strategic partner now. So ARM, the software and hardware foundation for TinyML. DeepLight, we use AI to make AI faster, smaller, and more power efficient. TinyML for all developers. EMSA Visual Sense, the I in IoT. GreenWave Technologies, enabling the next generation of sensor and hearable products to process rich data with energy efficiency. Gruity Incorporated, software development services for TinyML solutions. ARM partner, by the way. HOTG, distributed infrastructure for TinyML applications. Latent AI, adaptive AI for the intelligent edge. Maxim Integrated, now the part of analog devices. So Maxim Integrated, we're enabling edge intelligence. Quixo AutoML, automated machine learning platform that builds TinyML solutions for the edge using sensor data. Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. And special thanks to one of the chiefs of the TinyML community, Evgeny Gusev, who actually helped to establish TinyML community in our beautiful country, Ukraine. Reality AI, add advanced sensing to your product with Edge AI and TinyML. Broad and scalable edge computing portfolio, microcontrollers and microprocessors from the Renaissance, sorry. Seed Studio, the IoT hardware enabler. SenseML, builds smart IoT sensor devices from data. SynSense, builds sensing and inference hardware for ultra-low power embedded mobile and edge devices. Sentient, deep learning solutions for TinyML and Edge AI. And I'd like to remind to everyone that next TinyML talks will be in the next year on January 4th from Cedric Nukteren, software engineer from Plumber. He will be demoing the world's fastest inference engine for ARM Cortex-M at 8 a.m. Pacific time as usual. And if you are interested, please contact talks@tinyml.org. once again, thank you very much for the participation. I wish to everyone a very happy new year, a very happy holidays, and thanks a lot to the whole TinyML community. Have a great day or a good evening, depending on where you are.